I'm going to talk about the security of 3D web browser extensions, in particular the sort of most popular one at the moment, WebGL. All good? Just a bit of background. Sorry. A bit of background on myself. I work professionally in the security field for about 10 years now, and I do research, I do programming, I do vulnerability development, all that sort of stuff. And I have a particular interest in sort of esoteric platforms, games consoles in particular, and the last major conference I presented at was the Chaos Computer Congress in Berlin, talking about cracking the PlayStation Portable and owning Sony's security model, which seems always topical at the moment. So this talk comes out of some research that me and a few other people at Context did into these 3D web extensions. And basically, what can we actually do with what in the end was the research showing us we could do? We could potentially crash your computer, seems reasonably nasty. We can also steal images of your logged in web pages or even your desktop, depending on the operating system. And we also found issues which could then ultimately lead to remote code execution. So this is why we're here. Who doesn't want to play Star Wars Arcade in the browser, delivered straight to your computer, not having to download anything? It'd be wonderful. Now, 3D graphics has come on amazingly since the early 80s, where you used to get wireframes. You've now got thousands and thousands and thousands of polygons all shown on screen at the same time. And this is produced basically because commodity hardware has come on so much, commodity graphics hardware especially, so that you can have hundreds of cores, each running at multiple gigahertz, a couple of gigs of RAM, just in something you can walk into a computer store and pick up. So it would seem ideal that if you could deploy this via a web browser, it'd be great. And this is where WebGL comes in. Now, WebGL is a standard, or for what you want to call it, which basically allows you to produce accelerated 3D graphics from the web, so controlled by JavaScript, all inside your web browser, and everything's great. And it's produced by a consortium. The standard originally is produced by a consortium, and then obviously has to be implemented by the individual browser manufacturers. So the two main browsers which are supported at the moment are Chrome and Firefox. And this is a real simple bit of script code which does some WebGL stuff. It doesn't actually do a lot, but basically the WebGL is based on the 2D canvas, the HTML canvas element, and it allows you to get, in effect, a 3D context, 3D object out of that canvas and render accelerated 3D graphics to it. And this bit of code basically sort of manipulates some a vertex buffer and just buffers that data. It doesn't actually draw much, but unfortunately the slide wasn't big enough to contain all the code to do something useful. And I don't need to actually tell you guys probably how you would actually potentially use this in a bad way. So obviously all you need to do is get someone to visit your site through whatever mechanism you particularly care about. So to get a bit of better understanding of the sort of security issues that WebGL can bring about, we have to think of actually how WebGL does its drawing, does its 3D rendering. So this is a very simple representation of the display pipeline which is used to take your 3D models and your 3D data and actually output that to the screen in some fashion. So first you have your 3D models, which is represented by our triangle and our cube, and that consists effectively of a load of 3D points, generally referred to as vertices. And the first thing it does, it has to push these vertices through a arbitrary bit of code, which is called a shader, to transform them into something which can actually be displayed on the screen. Now, this arbitrary code is something which you actually provide in your web page, and so it's written in a language called GL shader language, and it's a sort of C-style bit of code which is compiled on the fly by the WebGL implementation and is used to transform these vertices. The next step in the process is you need to take that sort of projected information and work out which bits of the screen you want to draw. And this is where rasterization comes in. So this comes out of the sort of classic idea of CRTs where you had single lines you drew on the screen, and you basically map out your polygon so that it has, you know exactly which pixels you're going to draw. The final major step in the process is the fragment shader. So once you've generated your individual pixels, your individual fragments, you then run another piece of arbitrary code, again written in this GL shader language, which takes each fragment in turn and assigns them a color. So this is run once per fragment, so potentially if you've got quite a lot of pixels you're displaying on the screen, it's going to display it, it's going to run your code a very, very large number of times. And then it goes through some basic code to generate the pixels, and that's what actually ends up on your screen. So this is an example of a vertex shader. As you can see, if you're used to the C-style languages, it looks fairly familiar. Obviously some interesting keywords in there. But all that code is doing is multiplying a vertex, which is a vector effectively, with a matrix and setting a particular value for that vertex. The rasterization, this is just a basic, as you can see, it's a load of lines. You work out where the lines are on the screen, and there we go, you've plotted your fragments. And then a fragment shader. This one takes a texture map, which is basically a picture you want to render onto that polygon, and samples it at particular points and says, right, I will assign that color to that pixel. But it seems a bit unfair to just talk about one technology. So as I go through, I'll also, the things we found in WebGL, I will try and sort of map that to some of the other popular technologies which are coming along. So Flash 11 comes with something called Stage 3D, which again is a sort of in-browser 3D API. And in Flash 11, I think, was just recently released. Silverlight 5 is coming along as well, and that also has a 3D API embedded in it, although it's still, I think, currently in release candidate. And finally, I've also picked Unity, and Unity is a 3D graphics engine which you can just write your arbitrary game for, and it has a web-based plugin which allows you to deploy your wonderful game on the internet. So we'll go actually into some of the security aspects of WebGL that we identified when we were going through our research process. And the first one we came across was remote denial of service. Obviously, denial of service could mean, in this case, we just break your web browser. Well, most people wouldn't really care that much. If they may be annoyed, but it's something they can just restart their web browser and continue on, and no one's particularly harmed by it. But obviously, I wouldn't be talking about denial of service in that sense if it was actually that simple. So we just look at the standard. And this is actually a cutout of the WebGL standard. You can just download it from the Khronos group's website. And I'll highlight some interesting statements they've made in it. Firstly, apparently by a combination of shaders, geometry, you can cause something to take an undesirably long time to render. It seems a bit euphemistic for something which potentially could be bad. Now, it does then state that this long-running drawing call can not only cause your user agent to fail, so your web browser, but also loss of interactivity for your entire Windows system, i.e. your computer's user interface basically falls over or locks up and you can't do anything. But of course, it's not all too bad, because apparently it's all expected to be better in time, and in the future everything's going to be wonderful and it's all going to get fixed. So to understand why this is a problem and why this is possible, we just have to quickly go through how the OS graphics stack actually is implemented. And so I've picked out 5 main areas in the OS graphics stack, which you'll find pretty much in any major operating system. And at the top level, you've got your user programs. So this is your Silverlight, your Flash, your Unity, or your WebGL. And these are providing 3D services to some potentially untrusted person. They then talk to a second layer, which is your 3D graphics APIs, and this is where the well-known sort of OpenGL API sits, and also DirectX is also at this level. And this is the last part where you have like a standardized interface to your 3D graphics. That then converts it into a more lower level representation and passes it along to an OS component which schedules this this bit of drawing to be drawn on the screen. Now, obviously, a modern operating system, you have potentially multiple users of the graphics card. You could have a video playing, you could have a 3D game playing at the same time, but you've only got one graphics card and one screen. So in order to facilitate that, we have to queue them up, schedule them up so that you can then render them in order. So that comes down to, once the schedule has decided to try and render something, it passes it to the graphics driver, which is implemented by the hardware manufacturer, and finally, it gets your hardware, and hopefully, if all going well, it's displayed a nice picture on the screen. But unfortunately, there's a potential problem in this scenario, in that your scheduling mechanism and your graphics card hardware is generally not designed to be preemptible. So once you've started a running job, so once you've tried to render some 3D graphics to the screen, if it takes too long, in the general case, it's not possible to evict that piece of code from the graphics card. And depending on what operating system you're running, it does potentially different things. So this is an OS comparison. On XP, it does the worst thing it possibly can do and crashes. Which is a bit, it's actually specific check put into XP that if it takes too long to render, we're just going to blue screen the machine. Now Vista and 7 seem to have improved on that by it will now reset the graphics card if the rendering process is taking too long. Although if you really go at it, you can still cause the box to crash through this mechanism. Linux itself doesn't actually have any OS component which is doing the scheduling. So it's actually the graphics driver in this case which is handling this lockup, and will also do a similar thing to Vista and 7 where it will reset the graphics card, although it's obviously dependent very much on the graphics card you're using. And finally, OS X. OS X is heavily reliant on 3D graphics for its GUI. Can't work very well without it. And basically, if you do this in a web browser, you cause the GUI to freeze. Now, the machine hasn't crashed. You can still access it via SSH or other mechanisms, but most people probably do not have access to that and allow them to kill the offending process, which is causing your GUI to lock up. Now, how easy is it to do this? How can we produce something which takes too long to render? Well, technically, this would work. If you wrote a shader which does nothing, an infinite loop, basically, in theory, that would actually cause it to fail. Fortunately, both Chrome and Firefox will not accept this as a valid shader. It has an internal checking mechanism which validates whether you can get into potential infinite loops and will make sure that the WebGL rendering process cannot use it. But that doesn't mean there's no other way of doing it. As the standard stated, you could have a shader or you could have geometry. And this is basically some sample code provided by the Khronos group, which throws loads and loads of geometry at the graphics card, and on the particular machine will cause the machine to freeze. Now, fortunately, the demonstration actually has a nice dialog box. You can say, do you want to get owned or not? Yes, please, thank you. But obviously, an attacker, in any sense, wouldn't need to prompt you for getting taken over. So I'm going to try and show a video of this, because DOSing my machine while trying to do a presentation is probably unwise. So this is me running the Khronos group example. So this is just publicly available on the internet. You could get someone to redirect you to it, and you can click OK to get yourself to fall over, and hopefully it blue screens. And apparently we crashed in win32k.sys, which doesn't sound a particularly good thing to crash in. But in reality, in that particular case, that is just the standard XP mechanism saying, oh no, the graphics card's locked up, I can't do anything. So, oops. Just come back up. So what about everybody else? Well, Silverlight 5 is definitely vulnerable to this because one of the Mozilla developers who does some of the WebGL development, publicly put out a example Silverlight 5 application which did exactly this and DOSed the machine in exactly the same way. Flash is a bit, I couldn't quite work out whether Flash was or wasn't. They've done a lot of things to make it slightly different to most of the other 3D APIs which are being provided in the web browser. And their shaders do not provide loops or anything like that, so I couldn't actually get it to do the DOS, but it might be possible. And for Unity, it's almost certainly possible to do as well. It supports full shader languages, so it's probably bad as well. Now hopefully we can fix this. One of the ways, we can wait for our better graphics cards to come along as the standard sort of implied, and it will all be preemptible and all play nice, and nothing will ever crash again. But there's also a few other things which the Khronos group recommend. You've got a special web OpenGL extension which will provide the same features as the sort of Vista 7 Linux sort of, will just reset your graphics card if something fails. Now fortunately, one of the things it also adds is it will blame you, it will tell you whether you were at fault for causing that to crash, and therefore a web browser can potentially go, right, okay, no more WebGL for you, I'll stop doing that. There is apparently a version 2 of this which will solve even more problems. Unfortunately, I couldn't actually find much details about what version 2 fixes over version 1, so hopefully that'll come about soon. And I suppose another thing, WebGL is designed off OpenGL, and you could actually model your API to perhaps get around this denial of service condition, but realistically it would be a difficult thing to do. So the next bit I'm going to talk about is cross-origin images. So this is something which, when I looked at the standard, I sort of immediately picked up on and thought, oh, that could be an interesting thing to look at. Now we all know images are incredibly important for the internet. It would be pretty much the most boring place on earth if all you could see was text. You couldn't have all your images. And especially it's a very useful feature that you can include images from anywhere, any accessible web page. But the reason it's possible to do this, whereas you couldn't just include arbitrary HTML from another site, is because JavaScript or any of the other APIs traditionally couldn't access that content. It may be able to get some basic metadata about the content, such as the size, but apart from that, you couldn't get the actual data out. But the canvas element changed all this. The canvas element came along and said, hey, you can draw, you can pull in images from remote content, you can draw them onto this canvas, and then you can actually get the image data back out. You can just read the pixels out of the canvas. So in order to get around this, they designed Canvas so that it had a origin clean flag or a dirty flag, depending on how you want to look at it. And so if you use local resources, such as this piece of sample code, you can read out the pixel data and it's all fine. However, if you decide to pick an image from some other random place, it will cause a DOM security exception to be thrown, and you can't read the data anymore. It should all work fine. And so WebGL, being based on Canvas, thought, hey, well, we can implement exactly the same thing. If you use a texture, a remote picture, for your 3D graphics, we'll just set this origin clean flag, and then you can no longer read out any data from the canvas. And that should all work beautifully. And this is sort of an example of a Flickr viewer which allows you to read cross-origin images and display it in a nice fancy 3D environment, and click on it and you can see people's Flickr sets. But it turns out that there is something else which can read texture data, and that is the shaders. I've already said the shaders need texture data to be able to display texture map polygons, and so because the shaders can take different amounts of time depending on the data you feed into it, you can do a timing attack against it. So in this particular case, this bit of shader code, depending on the brightness of a pixel in your texture, takes a different amount of time to run than depending on the brightness. So by doing this, you can effectively measure the value of a pixel. And so indirectly, you can actually read out cross-domain images by using this as a timing mechanism. So it seemed to work quite well. You can obviously measure how long a drawing routine takes to run, because there's an actual method you can call which says, wait until I have finished drawing. And surprisingly, I found that the date time objects in both Chrome and Firefox really worked actually quite well. They were very accurate for at least the sort of timescales I wanted to work under to do this timing attack. And then all that data can be sent back to the originating server, and you've stolen somebody's images. And that images could be internal presentation data or anything else which you would not normally be able to access from an attacker's point of view. So I can show a very quick demo of this. Obviously, this is something which has been fixed in the latest versions of Firefox and Chrome. It's no longer possible to actually do the cross-domain image stealing. And so obviously, on the left-hand side is our image we're trying to steal. And it doesn't have to display the image. That's just to give you an idea of how it's progressing. And then on the right-hand side, we've actually got the data we're reading out from that timing attack and rendering it into a canvas. Obviously, you can see it takes a bit of time to run, but it is actually stealing what I would consider a sort of a reasonable representation of the original data. Just skip ahead briefly, and it can just go on. Now, of course, you don't have to steal the actual data itself. Because you've got access to the entire texture, you can just compare that image against a reference image. So, for example, in Firefox, there is a Mozilla protocol, which allows you to display system icons. Say, for example, if you have a PDF viewer installed, it will display a Adobe-specific PDF icon, and so on and so forth. Because that's now cross-origin, you would not normally be able to read that information out. But by using this, you could just infer, based on just what data you've been sent, whether they have or have not installed Adobe Reader. So, as for everyone else, well, basically part of the problem is just the permissiveness of the web browser to allow you to read these cross-domain images. And so Silverlight and Flash generally use the sort of cross-domain policy files to block you from reading things you shouldn't be able to read. However, Unity actually uses exactly the same model WebGL uses and sets a dirty flag if you use a cross-origin texture. And so basically Unity should be basically vulnerable to the same exploit. Now, as I said, it has been fixed in the latest versions of the browsers, and it's been fixed by using CORS, or cross-origin resource sharing. And so now WebGL will only load cross-origin textures if CORS is implemented and the server says, yes, you're allowed to read that image. And that is now implemented in the latest versions of Chrome, and Firefox 8 finally added that as well. So the next thing we identified was information disclosure, basically through memory separation and implementation issues relating to WebGL itself. So this is sort of a rough diagram of how VRAM, which is video RAM, which is sitting on your graphics card, is used. And basically, it's used for everything. Everything's just squished in together into one big block of memory, and so you've got your image data, geometry, compiled shaders, all that sort of stuff, all stuck into the same bit of memory. Now, how does, say, OpenGL, which obviously you can allocate textures, you can allocate frame buffers, how does that separate that out between processes and individual users of that API? Well, it doesn't. Basically, for performance reasons, it doesn't really make sense to mandate that the API has to, say, clear a frame buffer to 0, when basically most 99.99% of applications is just going to clear it immediately afterwards. It seems a complete waste of performance to do so. So each manufacturer implements their own OpenGL API, and potentially that changes what information is leaked depending on the particular implementation. So WebGL has to do something about this. It can't just leave that up to the underlying API in the hope that it will all work perfectly. So the WebGL standard specifies that basically if you allocate say a frame buffer or a texture buffer, you have to clear it to 0 or clear it to a known value. And this is what WebGL specifies. You must always have initialized values, and you must initialize your frame buffers to 0, your render buffers to the default clear depth, all that sort of stuff. And that's all fine. That's exactly how it should be. But of course, you've actually got to implement that in WebGL. It's not something the API provides for you. So how do we know whether we've met the WebGL specification? Well, there is actually a set of conformance tests you can get from the Khronos group, which run through many, many different tests, work out what actually, whether you meet it or not, and hopefully at the end you get a pass rate, and in a proper implementation you would expect everything to pass. However, when we did this test on different browsers and different operating systems, we got wildly different results between them. Some would fail. You would have differences between OSs for the same browser, which seems a bit odd because there shouldn't be much reliance on the underlying OS for how WebGL implements some of its functionality. So when we ran this, we fairly quickly identified a particular failure which looked potentially interesting. And this was related to whether, when you resize the canvas element in the document, whether it clears its value to 0 or not. So this is a bit of code from Firefox, because it was in Firefox we particularly identified this issue. And the question really is, can anyone spot the bug? I'm not expecting anyone to spot the bug, to be fair, because the bug is not what's in that code, but what isn't in that code. So this is roughly how it's supposed to work. OpenGL, which Firefox is using for its 3D rendering API, has basically a global state. So you set up certain values in the global state, and then you can call methods to do certain things. And clearing is one of those operations. You've got a special color which you can store in the global state, which says what color you want to clear things to. And then once you've set that, you can then call a second method which says clear that frame buffer, and it will write that pixel value to the frame buffer. And when you do that, your frame buffer becomes 0. Everything's hunky-dory, there's no problems. Unfortunately, OpenGL is a bit more complicated than that. And one of the things which the clearing code didn't take into account was that you can set a color mask. Now, the color mask basically says which pixels do you want OpenGL to render to a frame buffer. And so you can selectively block whether you want red, green, blue, or the alpha channel to be written to anything you call GL clear on or any other primitive mechanism to write to the frame buffer. And because WebGL is very much based on OpenGL, the Firefox implementation, where possible, uses shortcuts to just reuse any OpenGL primitive. And so it turned out that the color mask that you can set in JavaScript is basically used in the same context as the thing doing the clearing, the supposedly secure code which is clearing your frame buffer. And so by setting the color mask in JavaScript first, resizing the canvas, you end up doing that. And all the writes are blocked, and then you've got whatever data was left in that frame buffer. At this point, WebGL has no idea you've done anything wrong, and you can read out that data at will. And this is a bit of JavaScript which exploits that issue. So it's not a massive amount of code, but it was quite easy, it seems, to something to miss when actually doing the testing. And did it work? Reasonably well. So this is a picture of OS X, where we've got a confidential document on our desktop, and by doing this mechanism, we've been able to steal data off the desktop, so out of VRAM, and we can see your confidential document, and it's all bad. Unfortunately, just stealing that data arbitrarily is difficult. It requires a user to sit there and sort of work out whether that kind of looks like part of your desktop, which isn't particularly the most efficient way of, if an attacker was wanting to use this, it wouldn't be particularly useful. You could do some image processing to try and work out whether it kind of looked like say an OS X window, or particular, whether it looks like a font. But that was a bit more effort than we were willing to put in. So we came up with this other idea. Our Firefox guru, Paul Stone, came up with a mechanism to try and steal iframes. So one of the first things we needed to do was get that iframe picture into memory somehow. We really needed it in memory so that we could steal it. So he used this mechanism, which is part of Firefox, which allows you to do transforms on arbitrary DOM elements. And in this particular case, we're doing a 180-degree rotation and doing that a few times. And this, we found, actually pushes an image of the iframe into video memory. But that still doesn't really help us. We had the problem we couldn't identify what we were looking for before. So why can we now identify it at this point? So one of the things we then did is apply SVG filters. Now, SVG filters, you'd assume was for SVG. You wouldn't think you could just do it for arbitrary DOM elements. But it turns out you can. SVG filters allow you to adjust the color space of a particular DOM element, even though you can't directly access the pixels in it. And so the first thing we did was try and make a bit of space in the color information so that we could then do something more interesting. So the first trick was we could just take the brightness of that pixel, stuff it in one of the color channels, and so we can now potentially read out that brightness value. And now we've got plenty of extra space. We can actually set one of the other color channels, say the red color channel, to a particular random value we've chosen. This can then be used as a keying mechanism to actually read back out the texture information that we're trying to get hold of. We've obviously got another couple of colors left free, so we encoded YUV color in there, so we had 4 bits per color, and we could get a reasonable color representation back out. And you could also do position information so that you could properly reconstruct the blocks of VRAM so that it all looks pretty. So I've got a very simple video of us doing this. So we wanted to come up with something which stole your LinkedIn or an image of your LinkedIn profile. And so this is just going through and showing Bob's profile. This is his own private profile. So the next thing is, obviously, that user must have logged into LinkedIn. So we get them to go to our arbitrary site, which is, at the moment, has no images stored on it. Obviously, hopefully they don't see this, but that's an empty directory. So by taking them to our bad site, which there is absolutely nothing to see here, there's nothing suspicious about this page whatsoever, but it just sort of sits there and shows you a nice image of a U-boat in the Thames. But if we go back to our store, we've suddenly found we've got some images in there. And these are our stolen images, which we've basically pulled off by doing this iframe, doing it completely in the background so you can't see that it's even doing it, and then using this bug in WebGL to effectively, or this bug in Firefox to effectively steal our texture data. Unfortunately, we somehow managed to get a Google search page up first, but it does actually show our LinkedIn profile. So this is basically an implementation issue. The Firefox guys missed a bug in their implementation, and effectively everybody could be susceptible to it. You can't say possibly Silverlight or Flash have better, Microsoft or Adobe have better coders, so they're not going to have implementation issues. I think we all know that not to be true. And so yeah, everyone could potentially be affected by this. But WebGL does have at least a special place because it's so similar to OpenGL, and so there is the temptation to have shortcuts, which you end up, this implementation issue was due to the fact that the development was shortcutted by going directly to the OpenGL implementation underneath it. Another issue which came out of looking at the conformance test was there was no actual indication that the failure we identified was a security issue. all tests pretty much were determined to be the same, and so there was no way really for the Firefox developers to really say, oh, that was definitely something we needed to look at. And unfortunately, they also disabled these tests for OS X and XP because they kept failing, so they just disabled the tests whenever they ran the conformance suite. Very unfortunate thing to do. So this is basically the last thing I'm going to talk about. So as we're looking through WebGL specifically, one of the things which immediately comes to mind is you've just massively increased your attack surface. You've got all the 3D graphics hardware, the 3D drivers, the 3D APIs, all getting involved in this particular process just to render a few fancy polygons. And it's a massive increase. And graphics card manufacturers haven't traditionally been the most secure developers available because they're not focused on security. They really want performance. In the end, if you get an extra frame per second by doing some dodgy hack in your graphics driver, that's going to have a much greater impact on your client base than any sort of security aspects you want to bolt in. So I gather, based on what you actually find, is that the Chrome and Firefox developers have found this to be a problem. And have implemented basically a blacklist of bad configurations, so drivers and particular hardware, but also a whitelist of good configurations they know to be good. Apparently the whitelist was because on Linux, especially, you can actually crash just trying to find out whether you had a blacklisted driver or not, which is a bit unfortunate. But of course, this doesn't seem a very tenable solution for the future. Firefox 8 just recently had to do a hack around for the OS X Intel drivers, because realistically, they can't just ban a large proportion of OS X users from using WebGL. It would be too great an issue. And also, as an anecdotal thing, I submitted a memory overwrite bug to the Mozilla team, and about 2 weeks later, I found my configuration to be banned because they had trouble reproducing it on anything else. So about the only thing you can say is, well, it's probably your configuration which is at fault, and we'll just ban you. Doesn't seem a very good solution if you're trying to use this in any commercial scenario, because these actual blacklists come down outside of the usual patching cycle. They can be automatically updated by the browser developers without you even updating your version of your browser. So you could find your medical imaging application, which you've spent so much time crafting in WebGL, suddenly stops working because someone somewhere has found a bug in your graphics driver and configuration. And that doesn't seem a particularly good thing to do. And it's not just WebGL which does this. Silverlight does it, and presumably Flash also does it, and just will block certain configurations. In fact, Silverlight 5 can't even run on XP with 3D graphics, because obviously if Microsoft don't trust it, then you know it must be bad. There's also a problem of old code. To get this to market, we try and reuse as much as possible. So we were reviewing some of the code which is actually associated with WebGL, and one of the things which comes up is the Angle project. And the Angle project is an implementation of OpenGL for Windows, which actually sits on top of DirectX. Because Windows can be notorious for having really bad OpenGL implementations. So in order to get around this, they'll have, I think it's actually a Google project, and basically came up with their own implementation for it. And both Firefox and Chrome use this code. Now, we identified when looking through it, just as a source code review, while most of the code was actually quite good written code, relatively modern code, probably actually very modern code, for some reason, in part of the shader compilers, they put in some 9-year-old NVIDIA code. Okay, that may or may not be an issue. Of course, this code probably was never designed for being used in a web browser or in an untrusted scenario, and it turned out it wasn't the best code audited. And so we found a number of issues which have been pushed through and fixed in Angle or fixed in Firefox. Basically allows potential for remote code execution, heap overflows, all that sort of thing. And just because trying to get it there as quickly as possible, we've just thrown in some 9-year-old code. And we cannot deny all new technologies are going to have issues. But in the sort of like month of investigation we did, we've got at least 5 CVE numbers out of it. And we're not the only ones looking at this sort of thing. There's been a number of other issues which have been reported in WebGL, unfortunately. And let's face it, everyone else is going to be susceptible to this. If everyone is using their 3D graphics APIs, the underlying hardware acceleration, you're going to have increased your attack surface by a fairly sizable amount. So what conclusions can we actually come from this? Well, certainly it will only get better from here, and people seemingly want to play Angry Birds in their web browser, and can we blame them? But perhaps the maturity at the moment is a bit lacking. It's not quite just there yet in terms of security. And the trouble is, if sort of like we run headlong into implementing 3D graphics in the browser without perhaps waiting for the graphics card manufacturers to produce something a bit more robust in these scenarios, then we're going to have issues. So is there much you can do? Well, if you're really, 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 really paranoid, and you think someone may try to attack you, you can disable any of these technologies. WebGL, there's a way of disabling it in the browser, and you could just actually not install plugins. I know to some, Flash may actually not be an optional component, but technically it still is. You can still disable it. NoScript as well can also be used in Firefox. It will actually selectively block WebGL, and obviously will also selectively block any of the other plugins which may be used in this. So I'll finish up with some thanks. Obviously, thanks to the people in Context, especially the people who worked on it. The Mozilla security team have been great, so they've been very responsive to the issues we've given to them and fixed them in a timely manner. And obviously, can't get away without actually thanking Ruxcon as well. So, any questions on that?
Shader code, C type language, it looks that, from what I understand, that compiles in the user code, the implementation specific, is that right?
Yeah, that is compiled by the WebGL API. So it's provided in your web page as the C code, C-style code, and it has to be compiled by WebGL itself.
And what does it compile to?
It's very specific to the particular platform. For example, if you're using Angle, which is this OpenGL over DirectX system, it actually compiles to the DirectX shader language style, and then the DirectX shader language will compile to the a sort of binary format which is specific to the graphics card or the manufacturer which is implementing that.
Will it actually run that code? Is that
That's the graphics driver itself, and that's why obviously if you can get a very long-running shader code, it will sit on the graphics driver spinning away and potentially cause issues. Yep.
You made no mention of HTML5.
Hang on, is someone asking a question without a talking stick?
Sorry.
Sorry.
Put your hand up for me, who had the question? There we go.
I was just wondering whether HTML5 addresses some of your security concerns regarding the way three-dimensional images are rendered.
In terms of at least WebGL is entirely independent of HTML5. It has, while it's using the canvas element, there's nothing particularly in HTML5 which makes any sort of difference to the 3D security aspects. Because WebGL isn't actually currently a standard as part of W3C or anything like that. So certainly things like CORS, the cross-origin resource sharing, is something which will be coming in with HTML5's work, and that does then eliminate the issue of the sort of cross-origin stealing. But that also required a change to WebGL to basically say you must use CORS. You cannot just do as we already did, where you just set the flag and say, well, you can't just read the pixels.
Thank you.
Yep.
We've got some time for some more questions. Just put your hand in the air and you can ask any question you like. What's your favourite colour?
Definitely black.
Black? Yeah.
Not that it's really a colour, of course, but...
Well, you know. No more questions, guys? Peter, you have a question, mate? No? He already knows everything, doesn't he? All right, well, give it up for James. Thank you very much, mate.